Assalamualaikum and hi everyone. My name is Amna and today our group will be presenting our innovation called Self-Steering Thermal Mailbox. The Self-Steering Thermal Mailbox is an innovative food container designed using principle of thermophysics and rotational mechanics. It helps maintain food temperature, reduce heat loss, and promote more even heat distribution. In our busy daily life, many students and workers face the problem of eating cold or unevenly heated food. This innovation aims to provide a practical solution for students and workers who need warm meals throughout the day. We will cover the need, approach, and benefit of our innovation on the other slide.
The biggest issue with on-the-go meals is that they get cold quickly and heat unevenly when left sitting. This affects food quality and safety. Our device is designed to fix the problem that everyone faces. From thermal physics perspective, there are three distinct heat transfer mechanisms. First, conduction. Second, convection. And the third one is radiation. For conduction, direct thermal contact between the food and the internal walls of the container. For convection, air currents moving within and around the food. For the radiation, electromagnetic wave emitting from the food into the surrounding. Due to thermal equilibrium, hot food will always seek equilibrium with its cooler surrounding. Overcome the low thermal conductivity of food and avoid cold spot, this device integrates rotational motion. This mechanical movement passes the static gradient that causes unevenness. As the internal mechanism rotates, it continuously shifts the food mass, ensuring that heat is dynamically and uniformly distributed throughout. By combining the principle of thermal physics with rotational motion, this device provides reliable, evenly heated meals for students, workers, travelers, and anyone who needs a hot meal on the go.
Now, let's move on to the component of approach. Let's see how our mailbox solves these problems. How the system works. Starting with thermal physics, the heating element at the base of the box heats the fluid via conduction. At the same time, warm air inside the sealed compartment circulates via convection. Both of these mechanisms work together to continuously supply heat to the food, preventing it from reaching thermal equilibrium with cooler surroundings. For rotational mechanics, a motor spins the rotating tray using torque. The tray rotates at a controlled angular velocity, which breaks the static temperature gradients inside the food. This means every part of the food is constantly moved through the heated zone, resulting no cold spots. Now let's focus to how these physics concepts are applied. For thermophysics, conduction works because heat naturally flows from high to low temperature through the metal base of the box, transferring heat directly into the food. Convection works because warm air rises and circulates naturally around the food inside the compartment. The heating element also continuously resupplies heat energy to oppose thermal equilibrium. This is what keeps the food warm over the time. For rotational mechanics, torque is produced because the motor exerts a force at a distance from the center of the tray. This torque drives the rotation. The angular velocity then keeps the food constantly moving through the heated zone, ensuring even and consistent heat distribution throughout the food. Next, there are three equations applied in our system. First, Q equal mc change of T. This calculates the heat energy needed to maintain the food temperature, where Q is the heat energy, m is the mass of the food, C is the specific heat capacity, and change of T is the change in temperature. Second, torque equal Fr. This is the torque produced by the motor that rotates the tray. F is the force applied by the motor, and R is the radius of the tray. And last one, omega equal theta over T. This is angular velocity of the rotating tray. Theta is the angle rotated and T is the time taken. This equation tells us the speed of the tray rotation. Finally, the outcomes and effect that we observe from our system. Tray rotation results in even heat distribution with no cold spots in the food insulation walls, reduce heat escaping from the box, resulting in less heat loss. The heating element continuously supplies heat, which delays thermal equilibrium and keeps the food warm longer. The temperature sensor automatically stops the heating once the food reaches 60 to 70 degrees Celsius, preventing overheating. And last one, the LCD display shows the real-time temperature of the food, so the user always knows the current condition of their meal.
Let's take a look at our prototype design, starting with a model design front view, engineered for portability. The exterior features a top handle, a single power button, and a USB charging port. To keep our user updated, an external LCD display tracks the real-time internal temperature that is adjustable to our preferences. And next, we have the system status, while the heat vent slots manage airflow safely around the bottom. And moving inside, the cross-section view, the inner chamber is wrapped in a double-wall insulation layer to prevent thermal energy from escaping. At the base, the heating element provides warmth, while a compact DC motor powers up the rotating tray. Looking from the top view, this tray is partitioned into 5 distinct food compartments because different foods have different heat capacities. The tray is completely rotatable, ensuring every compartment passes over the heating zone. As shown in the power system diagram, a rechargeable battery fits a temperature controller, which simultaneously drives a heating element and a DC motor, while sending the real-time data straight back to the LCD display.
Our device offers 4 major benefits. The first one is uniform heating. Second one is enhanced energy efficiency. Third, enhanced thermal insulation. And the last one is eco-friendly. For the first one, which is the uniform heating, by optimize the mechanic of rotational motion, we ensure that heat distribution is completely even throughout the container and eliminating cold spot entirely. Second, the device features enhanced thermal insulation. This design actively minimizing heat loss caused by conduction and radiation, keeping the internal environment stable. Because the insulation is so effective, it unlocks our third benefit, which enhanced energy efficiency. The device doesn't require massive power. It only needs a small motor and low power heating element to maintain a constant temperature. Last but not least, our device is eco-friendly. It is reusable and self-contained system. Users doesn't need to buy disposable food packaging or buy food outside on the go. It also promoting a more sustainable and cost-effective lifestyle. By combining the uniform heating, enhanced energy efficiency, and enhanced thermal insulation, and the last one is eco-friendly, we created a device that is smart, efficient, and kind to the environment. Thank you for your time.
To wrap things up, the self-steering thermal mailbox brings physics out of book and into the real-world situation. By controlling the heat transfer by using rotational movement to eliminate cold spots, we have created an energy and time-sufficient, eco-friendly solution for anyone needing a hot meal on the go. And it's practical, it's sustainable, it proves that physics can solve our everyday problem.